All right, welcome. Today's lab, we're going to take a look at frequency response of active filters. Now, in the last lab, we took a look at RC circuits and RL circuits and saw that we can selectively use their impedance properties to get rid of some frequencies that we did not want. So we looked at we looked at passive low pass and passive high pass filters. Those filters from last week were called passive filters because the output of those filters were always either equal to Vin or less than Vin. Now, a while back in this class, we also looked at op amps. Op amps are primarily used, one of the ways we use op amps is by using their property as an amplifier. What that means is that the output voltage could be selectively controlled using a set of feedback impedance or resistance to be greater than or equal to the input voltage that we apply. So in other words, the output could be higher than the input. Now combining the gain or the amplifying property of the op amp together with the filtering property of RC and RL circuits, we can create what is known as active filters. These filters are called active filters because they not only allow you to tune the frequency you want to select, but also allow you to apply a gain to it. So let's get started first by looking at the op amp circuit. So here is one of the very traditional inverting amplifier topology. Right, so there is an input voltage coming in. Here's the input resistance. In this case, I have 1 kilo ohm resistor, and then there's a feedback resistor that's 10 kilo ohm. Now, if let's quickly recap the inverting amplifier properties and see what the transfer function of this particular circuit is. Okay, so we've been using the word transfer function when you do frequency response, so that's what we'll call it. So in order to analyze this circuit, we can go back to our ideal op amp conditions. Now, when I have negative feedback, I can assume this op amp is ideal, which that basically means is that there are two important properties. The first property is that the output voltage at so the voltage at this node, right, the plus node of the op amp and the voltage at the negative node of the op amp are the same. So that's what an ideal op amp states, that V plus is equal to V minus. So in other words, in our case, V plus is connected to ground. So that's 0 volts here, right? So that's 0 volts here. Now we would have VA, which is connected to V minus port, also equal to 0. So that's the first thing that comes from ideal op amp. So A is 0. The next thing ideal op amp says is that no current can go through the input terminals of the op amp. So that means the current coming in from this way, In can come in this way. Kirchhoff's current law says it'll branch out, but ideal op amp says that the no current can go into here, so all the current will go out this way. So based on these two rules, then we can apply Kirchhoff's current law at node A, and we can say that the In coming in into node A, there's only one path for it, which is this current called I out through that feedback resistor. Now, I in starts at V in and goes to A, so we can say V in minus A divided by R1, and I out goes from A to V out, so similarly we can write VA minus V out divided by RF. So this is what we have, right? We can substitute VA for 0 volts, so that's what we get. And getting rid of A, we have the following relation. Now let's rearrange things. So let's bring V in to one side and RF to the other. So we get minus V out over V in is RF over R1. Okay, let's rearrange this just a little bit because we've said that the transfer function is the ratio of the output to the input phasor. So in this case, the ratio of the output to the input is equal to negative RF over R1. So we have a negative sign there. So that's the transfer function. Now that we have the transfer function of this circuit, remember this is what we called gain before, and that's apparently the same as a transfer function. So now that we have that, what is the magnitude of this guy and what is its phase? Right? This is a fairly trivial example because if you look at this, here's my transfer function. What's the magnitude? Well, the top part, right? So when we think about phasors, we know that there's a real axis and an imaginary axis. In this case, it says RF and R1 both the RF and R1 have real impedance. So RF is 10 kilo ohm, R1 is 1 kilo ohm. So it's all in the real axis, right? So if I'm thinking about an axis for these impedances, RF and R1 both lie on this real axis right here. So they only have the real property. So in terms of magnitude in this case, then what we get is uh, the magnitude of this transfer function is simply the ratio of RF and R1. So negative, no negative sign, right? Because magnitude is about the absolute value of this. How about the phase? What does phase say? Phase basically says that here, so what do we have? If let's say on the phase, let's rewrite this, right? Phase is basically the angle of the numerator of the transfer function minus the angle of the denominator. Now, angle of the numerator. Well, let's say the numerator is minus RF. Well, what does that say? Well, that basically says that RF is right here. So this is RF right here with drawn with the red ink, right? So that's RF. Okay, so that's RF right here. And this with the purple ink is R1. Now RF is 180 degrees phase, right? So we can write this as, or we can think of this as negative 180 if you were to read it this way. It's minus 80 and 180 are essentially the same. So in the case of the uh, a denominator, we have R1, so the angle is 0. So we have an overall phase angle of minus 180, right? So here I have my magnitude of RF over R1 and my phase of minus 180, okay? Now RF over R1, if I apply a DC, 0 hertz, well, resistors have impedance that are frequency independent. So it doesn't matter whether I apply 0 hertz or 100 kilohertz, the impedance of a resistor is going to stay the same. So 10 kilo ohm divided by 1 kilo ohm is going to be magnitude of 10 in this case, and the phase angle for the first is going to be minus 180, and the phase angle for the other one is also going to be the same. Well, minus 180 is the same as 100 plus 180, so in this case I just wrote down 180. Okay, let's verify that this is in fact actually correct. So I created an amplifier. So I have an amplifier created right here. So here is that exact same circuit, DC volt, 1 volt applied. Well, with a gain, I expect the output to be 10 times higher. So now if I run this simulation, notice this. So when I run this simulation, I have input voltage is 1, but my output voltage is close to minus 10 volts. Right? That's exactly what we were expecting the uh, in terms of the output voltage. Now the magnitude, right? So the magnitude, so in this case, the magnitude is, the voltage is minus 10, but the magnitude is 10. Minus 10 basically just means it's out of phase with the input, meaning it's 180 degrees in phase. Okay. Now what happens if I use AC? Now here's my AC voltage being applied to that same circuit. Now if I run the simulation, okay, uh, it's easier to see the AC in a graph. So let me just show you the graph. Now what do I see here is that the green plot is the input voltage and the blue plot is the output voltage. Now the output voltage, you see the peak is at 10 volts. Now you also see that the output voltage is exactly out of phase with the input voltage, meaning it's 180 degrees out of phase. That's exactly what we saw right here. Okay, so now this, so far what we've looked at is simply an inverting amplifier, right? Now let's go add a capacitor to this particular circuit. So let's add a capacitor to the feedback network. So that before we had this, and now we're basically just adding a 30 nanofarad capacitor. And what happens now? Let's see. Now, the analysis that we did with the inverting amplifier is exactly the analysis we're going to use now. Now, in this case, I like to think of this as in the inverting amplifier case, the impedance in the feedback path was 10 kilo ohm. In this case, the impedance in the feedback path is basically this capacitor in parallel with the 10 kilo ohm resistor. So that's my impedance. So instead of calling it RF, I'm going to call it ZF. Okay, that's the impedance, right? So we already saw that the transfer function, now if I replace this with ZF, then the transfer function is basically minus the impedance of the feedback path divided by the input resistance R1, right? So here, impedance of a capacitor is given by 1 over j omega c. I'm not going to enter the values of c right now. I'm going to keep it as this. But what I see is that the impedance of the capacitor is in parallel with the 10 kilo ohm. So basically, I can get the overall feedback impedance as the impedance of the capacitor times the impedance of the resistor divided by the sum of those two. So just like parallel resistors, parallel impedance uses the exact same formula. So here is my feedback impedance. Right, so my feedback impedance, if I start writing this, GC is the impedance of capacitor was 1 over j omega c times RF divided by 1 over j omega c plus RF. Now, if we use algebra to just simplify this, the bottom part right here, I get the following. Right, now in this case, I have j omega c on the top, j omega c also here, so I can cross those out, and what I'm left with is a slightly easier looking impedance in the feedback path, which is RF divided by 1 plus j omega c times RF. Okay, that's my overall impedance of the feedback path. Now, let's go and substitute that here. So what do I get? H equals the impedance of feedback path divided by R1, and there's a minus sign there. So if I plug all of that in, this is what I get. And I just want to rearrange this a little bit, and I can write the transfer function as minus RF over R1 divided by 1 plus j omega c times RF. Okay, so here is my transfer function. Okay, next we're going to do is take a look at the magnitude as well as the phase of this transfer function, because there were some questions last week about that particular thing. So here is my transfer function. So the magnitude, again, let's take a look at the magnitude. I'm going to keep this real imaginary axis here just for reference point, because it sometimes helps see the phase relation and so forth. So the magnitude of the top, okay, magnitude of the top is just simply RF over R1, and the magnitude at the bottom is 1 plus, I mean, this is a complex number of the form P plus JQ, right? If I have P plus JQ, the magnitude of that is basically square root of P squared plus Q squared, right? So this is basically saying I have a place where I have a place somewhere here that's about 1 unit on the in the real axis. Okay, so sorry. I have my pen. I have 1 unit in the x-axis, so here's my 1 unit on the x-axis, and I have omega CRF somewhere in the imaginary axis, so that is my point 1 plus j omega CRF. So if I drew a straight line from here, imagine this is a very straight line going here. What is the magnitude of this? The magnitude is this square plus square of that. Take this square plus this square divided by the square root of that. So that's what we have here. So that's my magnitude right here. Okay, so that's my magnitude. Now the phase is again the phase of the numerator minus the phase of the denominator. We saw earlier that the phase of the numerator can be written as minus 180 or 180, depending on your preference. The phase of this guy right here, this bottom part is what we plotted here. The phase angle right here in this case is given by, if I drew a triangle, that angle would be the imaginary part divided by real part. So this angle is the arctangent of the imaginary part divided by real part. So that's what we have, arctangent of imaginary part divided by the real part for the denominator. Okay, so this basically leads us to, again, 180 is the same as 180, so that's what it leads us to. So let's fill in this table about the magnitude and the phase. So what happens if I have DC? When I have DC, DC is 0 hertz, so omega is also 0. So that becomes 0, right? So this bottom part right here, omega CRF, this part right here, that goes to 0. So RF over R1 divided by square root of 1 plus 0. In other words, it's just RF over R1. So RF is 10K, R1 is 1, so that magnitude is simply 10. How about the phase? Well, phase, 180 degrees minus arctangent of 0. Arctangent is 0 at 0 degrees. So 180 minus 0 is 180. That's so at DC, our phase difference, our magnitude is going to be 10, and my phase is going to be 180 degrees. All right, let's see if I built that circuit. So let's see if that's actually correct. So here's my DC. Here's my DC circuit built. I'm going to run this simulation. And what I see is that my input is 1. My output is still minus 10. We're close to minus 10. So minus 10, right? So what we're seeing is that the magnitude is still 10 and the phase difference is 180. How do we know the phase difference is 180? Well, because the output voltage is minus 10. That's how we know that the um, output voltage has a phase of 180 degrees. So we verified the DC one. Now for AC, for 100 kilohertz, so let's say 100 kilohertz, well, let's see, 100 is a big number. 100 kilohertz is 100 times 10 to the power 3. Square of that is a much larger number. So if I really think about this whole exercise here, some numerator divided by some very large number leads to a small number. Okay, but let's actually plug in the real values and see what we get. So I have MATLAB here. I have C as 30 nanofarads, so e to the power minus 9. My RF is given as 10 kilo ohms, so I'm going to do that. And my omega is given as, oh, sorry, my frequency is given as 100 kilohertz, right? So frequency is 100 kilohertz. Okay, so that means my omega is 2 pi f, so 2 times pi times f. That's what my omega is going to be. And I'm going to basically enter the magnitude. So magnitude was RF over R1, which is still the same, RF over R1. So my magnitude is RF over R1. RF is 10 divided by R1, which is 10. So that divided by square root of 1 plus omega times C times RF, and this whole thing is squared. So I think I got all the closing parentheses. So what I get is, I got a wrong C, uh, uppercase C. And what I see is I get a voltage that's very small, 0.05. So I get a voltage that's very, very small. Okay. Similarly, what happens to the angle when omega is that? So let's see. Arctangent of, let's do 180 minus arctangent of omega times C times RF divide by 1. MATLAB, I'm using MATLAB right now, and MATLAB reports the angle in radians, so I'm going to change that to 100 in degrees, 180 by pi. Okay, so what I end up getting is 90 degrees as the angle. So I got a magnitude of 0.05 and an angle of 90. So what I have, 0.05 and and a oops, 0.05 and a magnitude of, sorry, phase angle of 90 degrees. Okay, you see, I have my MATLAB. What did I do here? E to the power 30 to the power minus 10, 30 to the power minus 9, RF. So I think I might have had an extra zero here. Okay, all right. Let's move on. So that's my magnitude and the phase. So we calculate the magnitude and phase at different frequencies. Now, finally, last week, a lot of you had issues calculating the cutoff frequency. So here is a quick definition of the cutoff frequency. Cutoff frequency is calculated as 0.707, by the way, which is also 1 over square root of 2. That's what 0.707 is. So cutoff frequency is the frequency that gives us 0.707 of the maximum magnitude of the transfer function. We just saw here that the maximum magnitude of this transfer function is when the bottom part is 1. In other words, the maximum magnitude of this transfer function is 10. So 0.707 times 10 gives me 7.07, right? So here's my magnitude of the transfer function. So if I substitute this omega with a cutoff frequency omega, so omega cutoff, that means this magnitude transfer function is 7.07. Okay, so I replace RF over R1, RF over R1. I replace that with 10 right here. And at that point, the maximum magnitude of this transfer function 10 times 0.707 leads me to this, which is at the cutoff frequency, right? Let's rearrange things. I basically bring 10 to this side and I get 0.707. 0.707 is also the same as saying 1 over the square root of 2. So let's verify that. 1 over the square root of 2 is 0.707. So instead of writing 0.707, I'm just going to write that as 1 over square root of 2. Now, if I compare these two expressions right here, equation right here, and cross multiply, what I end up with is at the bottom I have 2 and I have 1 plus omega cut off c times rf squared. Those must be equal. So I have 1 plus omega cut off crf squared equals 2. Bring this 1 on this side. So 2 minus 1 leads me here. Take the square root of both sides. So if I take the square root of this and the square root of this, I end up with omega cutoff CRF equals 1. So in other words, the cutoff frequency is equal to 1 over CRF. In fact, that's what we saw with a passive RC filter, because RC was the value of tau, and we saw last time that the cutoff frequency in radians per second was 1 over tau, right? So here I have, let's see what the cutoff frequency in hertz is then. That's basically equal to omega cutoff divided by 2 pi, and omega cutoff, if I replace the values of C and R, is right here. So that leads me to 530.5 hertz. Okay, 530.5 hertz. Now remember, at this frequency, okay, at this frequency right here, if my maximum voltage is 10, I should be seeing a voltage of 7.07. Okay, so what I'm going to do now is I have the circuit right here, and I am going to basically sweep this frequency. So this is my function generator. I'm going to ask it to do a AC sweep, and I'm going to say start at 1 hertz and go all the way to 1 times 10 to the power 10 hertz. So I'm going to basically start increasing this and recording the value of V out. Okay, so let's see what happens when I run this simulation. So I'm going to say start simulation, and all right, so here it is. So I'm going to get rid of some of these plots. V in plot I don't need. Uh, I'll get rid of the phase plot for now. All right, so here it is. So I have my output voltage. So apparently that's how the output basically changes uh, uh, over time, over frequency, by the way. So the x-axis is the frequency in the log scale, and the y-axis is the magnitude of the output. So here, what happens at DC? 10. So that's the maximum voltage, right? So we saw that the cutoff frequency was at 0.707 of the maximum, and we said it was at 7.07 volts. So I'm going to try and put this cursor, if I can, right at cursor. Let me see. Cursor 1 is going to give me on the y-axis 0.707. So I'm gonna look at cursor right here and say 0.707. So 7.07. Oops. Okay, let's say that. Okay, at that value right here, what is my uh, 0.707? So let me try and move this here. Cursor 1 is, okay, I see 7.07. I'm going to try and get me as close as possible. So I see right here that my voltage is 7.1 at a frequency of 523 hertz. So my voltage is 7.1 volts at a frequency of 523. So if I just can adjust this just maybe a little bit. Oh, it's finicky. 7.02 at 534 hertz. 7.07 at 530 hertz, and this simulation is confirming that at 7.02 volts, I can move it close to 7.07 with my cursor, but that's very close. So we see that we calculated our cutoff frequency fairly accurately. So what is the way to calculate the cutoff frequency? It's basically trying to equate the magnitude of the transfer function with 0.707 of the maximum value of that transfer function. Okay, so that's how you are going to go ahead and do the lab. A majority of what we talked about, what we're asking you to do in lab, I've basically gone over some of these things. So I hope you have a better theoretical understanding of the filters and are able to do the experimental part of the lab.